Greetings everybody. This video will hopefully explain to you how to work one of the sample problems I posted dealing with an inclined plane. And on the Georgia View site, it's titled Good Study Problem Inclined Plane. And again, I post everything in Word and PDF format. I've got the key posted, but let me go over the solution. Okay, so what we have is we have a 23 kilogram child, so we know the mass. And she's accelerating down a slide, so her speed is not constant, and she's accelerating down the slide due to this horizontal pulling force, which I've labeled P. So I know the mass of the child, I know the magnitude of the pulling force, I know the angle of the incline, and then I want to know if her acceleration down the slide is 2.57 meters per second squared. I want to know what is the coefficient of kinetic friction, mu k, between the girl and the slide. And the answer is mu k is 0.650. Remember, mu k and mu s, respectively, the coefficient of kinetic friction and the coefficient of static friction. Remember, they're one of the quantities that has no units. So in this case, and notice when I do this, when I say mu k and I draw a little arrow to the slide, don't let that confuse you. That's just my way of saying, hey, look y'all, there's coefficient of kinetic friction between the girl and the slide. That's what that arrow means. It's not a force, it's not a vector. It's just, hey, note to self. There's friction between the girl and the slide. Now remember, the key is with an inclined plane problem, you redefine your coordinate system such that the x-axis is parallel to the incline and the y-axis is perpendicular. And we always resolve mg, the weight of the object. You always resolve mg into its x and y components. Remember, when we say x and y, that is defined by the incline and the direction perpendicular to the incline. And so we're going to have to resolve mg into its components. And likewise, the horizontal pushing force, or pulling force, you can think of it as being in the original x direction. Just like you can think of mg as being in the original y direction. But now remember, inclined plane, we're not using those x and y. Their x and y are now defined, again, by the incline and the direction perpendicular to the incline. But think about it. If you resolve mg into its components, which is in the original y direction, if you will, well, likewise, you're going to have to resolve the pulling force P into its x and y components. Because remember, mg and p respectively, you can think of them as being in the original x and y. Well, again, we want to put that out of our heads. We need to get them into their components in the x and y defined by the incline. So let's go ahead and draw in mg and then do the components. Remember, we're going to have to draw the kinetic friction force Fk. We have to draw that correctly. And remember that because she's accelerating down the incline, that will be our positive x direction. But let's go ahead and let me bring up the key and let's look at all the forces. Okay, here's the answer key. Actually, here I actually got, the second time I worked it, I got 0.649, but we won't quibble between 0.650 and 0.649. Okay, anyway, here's mg, the pulling force, the horizontal pulling force P, that was given in the original figure. Okay, let's draw in all the other forces acting on the girl. Well, remember, there's her weight, mg. Always taking great care, clearly mg is in the original negative y direction. The pulling force P was already there. Well, remember, again, she's in contact with the slide, Fn. That's the normal force of the slide pushing on the girl. And by now we know that green vector representing my Fn, it's clearly perpendicular to the slide. Okay. Now remember, mu k, there's kinetic friction between the girl and the slide. Well, you have to draw in Fk, the kinetic friction force. Well, remember, and here, this arrow here, remember, this is not a force. This is simply telling you, hey, look, everybody, the girl is accelerating down the incline. Remember, that represents the positive x direction. Now, if the girl is accelerating down the incline, then Fk has to be directed exactly opposite, exactly 180 80 degrees opposite. So FK is directed up the incline. Okay? And remember, whatever direction something is moving on an incline, that is, by definition, that's the positive x direction. We know that by now. Okay, well, let's look at mg. And again, we don't need to reinvent the wheel. If I know that if the angle of the incline is theta, this angle here that I'm moving the mouse around, if that angle is theta, I know that the angle here that I use to resolve mg, I know that angle is also theta. And here, notice the angle here in when I'm going to the angle theta that I've used to resolve p, I know that angle is also theta. It's very basic geometry. All right, so now look at mg. Again, we don't need to reinvent the wheel. By now, it should be second nature. The y component of mg is given by mg cosine theta. The x component of mg is mg sine theta. Okay, Fn is fine. Okay, now Fk is fine because Fn is in the positive y, Fk is in the negative x. Now let's look at the pulling force P. Well, again, notice the y component of P is given by P sine theta because it's opposite to the angle. The x component of the pulling force, the x component of P, is given by P cosine theta. Now notice, remember, when a vector simply takes you from point A to point B. So the equivalent, that's how I know how to draw P cosine theta and P sine theta. I have to go positive x and then positive y. That's equivalent to taking the black vector P. That's why I know to draw P cosine theta is in the positive x and P sine theta is in the positive y. Now again, in all these inclined plane problems, you're never going to see an acceleration in the y direction. So let me go ahead and we'll get to that. So anyway, you want to make sure you're comfortable with how I drew the components of mg, how I got the components of p, why did I draw fk in that direction. And remember, the way you deal with inclined plane problems, again, because she is accelerating down the slide, that represents positive x. So mg sine theta is positive, p cosine theta is positive, and fk is negative. Very, very simple. Now in the y direction, nothing complicated. Fn and p sine theta are positive, mg cosine theta is negative. And for all the inclined plane problems, the y acceleration will always be 0. In other words, let's go to my y equation. That's why I know that Fn plus p sine theta, the two positive forces in the y direction, must equal the negative. So I know that Fn plus p sine theta must equal mg cosine theta. The other way you could write it, which I don't know that it really matters, is you could write Fn plus p sine theta minus mg cosine theta equals 0. But why not? To me, I just look at this figure. Hey, there's no acceleration in the y direction. Therefore, Fn plus p sine theta must equal mg cosine theta. That's equation 2. Now let's apply Newton's second law in the x direction. Well, remember, in the x direction, p cosine theta and mg sine theta, they're positive. Fk is negative, and the acceleration is obviously positive, and the acceleration is not 0. So sum of the forces in the x direction. Well, p cosine theta and mg sine theta, they're positive. Fk is negative. So this term right here, that's the sum of the forces. P cosine theta plus mg sine theta minus fk. Because again, just look at here. P cosine theta is positive. Mg sine theta is positive. Fk is negative. Well, remember, the sum of the forces must equal m times a. Okay, now remember, what is the problem asking for? We need to get the numerical value of mu k. Well, you want to remember, this comes in handy. Look at it in the box here. Whether it's static or kinetic, Fk is always equal to mu k Fn. Remember, Fn depends on the geometry of the problem, but this never changes. Fk is equal to mu k Fn. Well, that means that always mu k is equal to Fk over Fn. That's never going to change. Again, Fn depends, like here, we know Fn is mg cosine theta minus p sine theta. It depends on the geometry of the problem and how many forces you have. But anyway, so in other words, I want mu k is fk divided by Fn. So I'm going to solve equation 1 for fk, and I'm going to solve equation 2 for Fn, and then divide them. So equation 1 gives me fk is equal to p cosine theta plus mg sine theta minus ma. Remember, algebra is your friend, but it shouldn't be all that difficult to see. I've just, I bring fk to one side, it becomes positive. Ma goes to the other side, it becomes negative. Now, solve equation 2 for Fn. Fn is simply just basic algebra. Fn is just mg cosine theta minus p sine theta. Now, take those two expressions for Fn, and what is mu k? Mu k is fk over Fn. Well, in the numerator, that's my expression for fk. In the denominator, that's my expression for Fn. I know the mass. I know the acceleration. I know the magnitude of p. I know the angle. We know g is 9.80 meters per second squared. So plug in the values, and you get 0.649. Remember, coefficient of friction has no units, and remember, it has to be less than 1, so everything looks good. But the key is make sure that you understand what I'm doing with the pulling force P and what I'm doing with mg and how I get respectively equations 1 and 2. And that's the whole gist of this problem. Let me go ahead and save this video and get it posted.